Hello, here I am back again. I was interrupted in the middle of doing my fourth part of my function, writing the fourth function in writing the name Bob to demonstrate the project for you, and I had to pause for a few minutes, and so now it's a few minutes later, and I'm going to resume where I left off. So I got you back at that tilty angle, so you see me. Here's the page that I was working on when I stopped, and let me switch back around here. Let me pick up working on the project, writing the letter capital B. If you remember the three functions that I have written on the paper here, the vertical line x equals 1 from the domains and ranges, maybe I won't say those as I talk about it. The reflected parabola, -1/8 times x minus 1 plus 8, that quadratic function that formed the top part of the upper loop of my B. The bottom part of that upper loop I made with the cubic function, 2/81. So I showed in the first part of the video how I stretched by a factor of 2/81 to make the function go from 1,4 to 5,6. So in the last video I demonstrated how I fit that cubic, and then I decided I was going to do something a little bit fancier and something that we didn't cover in class yet with my next part of my function. To do something different and something to foretell the future, I'm going to graph the lower part of the bottom loop of my capital letter B that goes from 1, 0 to 5, 2 with an exponential function. So first I need to do a little bit of explaining about what is an exponential function and how to move it around the same way that I moved the quadratic and the cubic around to form the top loop of my letter B. So first of all, we'll study exponential functions in chapter 7. So you're hopefully some of you are already getting to that point on your homework where you've started working in chapter 7, where we learn about exponential functions and logarithmic functions in the same sort of fashion that we learned about our other parent functions, and we learned some of the same graphing strategies that we learned with our other parent functions with these classes of functions as well. So in chapter 7 we'll learn about the basic parent branch of the exponential functions, y is equal to b to the x. The number b is called the base of the exponential, so b is the base, and legal bases for an exponential functions are numbers between 0 and 1, or numbers that are greater than 1. So the only number that's not a legal value, well, you're not allowed to use negative values for your bases, and you can't use the number 1. So b can't be the number 1 because that's not an exponential function, that's a constant. But numbers between 0 and 1 as the bases of exponential functions give a decaying exponential, a function that's decreasing exponentially over time, and numbers that are greater than 1 give an increasing exponential function, a function that's increasing exponentially over time. Normally, exponential function has a couple of basic characteristics. If we were working on this in class and we were learning about getting ready to translate them, one important feature of an exponential function is the fact that all exponential functions, all functions of the form y equals b to the x, when x is equal to 0, pass through the point 0, 1. So when x is 0, by definition, any number raised to the 0th power is equal to 1. So all exponential functions pass through the point 0, 1 as kind of a general. On all of our other functions, we kind of studied the point 0, 0 as that point that we translated when we shifted left and right and those sorts of things. We moved the point 0, 0, but now we're going to have to move the point 0, 1, which adds a little bit of difficulty in the shifting left and right, or not the left and right part, but the up and down part gets a little bit more complicated. So remember, I'm going to try to go from 0 or 1, 0 to 5, 2 with an exponential function, or a function of the form y equals b to the x. Just like the other functions, we have three things that we can do to this kind of a function. We can multiply it by a constant in the front. We can alter the x's by adding or subtracting a number to x here in the power. That shifts the function left and right just exactly like our other functions. And then I can add a constant on the end to move the function up or down. Moving the function up or down moves this asymptote. The line y equals 0 is an asymptote for the basic unstretched parent function b to the x. So that asymptote moves up or down by adding a constant or subtracting a constant to the exponential function. So all in all, I'm allowed to multiply an exponential by a constant, add or subtract a number h to the x's to shift it left or right, and then I can add a constant k or subtract to move the function up or down, shifting this basic behavior. You can see the part of the function that I'm attempting to graph is going to be, I'm going to translate the part that started at 0, 1 and grows, I'm going to make it grow from 1, 0 to 5, 2. So remember, that's my ultimate goal, is to move it from 1, 0 to 5, 2. Well, exponential functions, you have to be a little careful with the translation part. I'm going to solve an equation to figure out the values of a and k here in just a second. I'm going to substitute in the 2 points that I know that I want the function to pass through. So number 1, I can use the first point that I want my function to go through 1, 0 and 5, 2. So I know two xy pairs that I can substitute into this relationship to solve for the values of a and k like I want in just a second. So I'm going to do the left and right shift first. So step 1 in my translation is going to shift the point 0, 1 to the point 1, 0 like I did on my graph. So I'm going to substitute in, for the number h, I'm going to substitute in the number 1. So my function is going to be basically a times b to the x minus 1 plus k. All right, so that shifts the point that was at 1, 0, 1, right 1 unit. Right now, the tricky thing about an exponential function is that I'm going to have to alter these two constants simultaneously, so I can't just subtract 1 to lower this point down 1. So I want that vertex point, or the point that I'm going to translate, to move to 1, 0, but I can't do it by just adding or subtracting a constant k here, so I have to do it in 2 steps. So step 1, when x is equal to 1, I want y to be equal to 0. So I'm going to substitute in that ordered pair into my function. So a times b to the 1 minus 1 plus k, I want that to be equal to 0. Right, and b to the 1 minus 1, or b to the 0, is 1, so that gives me the equation a plus k is equal to 0, or maybe I'll say it this way, that k is equal to negative a. Right, so I'm gonna solve for the constant k in terms of a myself. I probably could approach it the other way by solving k in terms of, or a in terms of k, but I think this might be a little bit easier. So I just found out by substituting in x is 1 and forcing the y coordinate to be equal to 0 that k must be equal to negative a, which means my function now is y equals a times b to the x minus 1 minus a. Right, so since k is equal to negative a. All right, now I'm going to use my other ordered pair that I knew. So when x is equal to 5, I want y to be equal to 2. Substitute that into my model right here. So I have 2 for y is equal to a times I'm going to back up here just a second, and this might seem a little bit confusing. What I did so far didn't matter what base I had chosen. I think when I very first started this whole project, I talked about the roundness of all of my letters and the fact that I was using a height of 8 and a width of 4. I was using powers of 2 to make some of my calculations a little bit easier. I hadn't said it in this current start of what I'm doing right now, but I'm going to choose that base to be 2. So the letter B that I've been writing instead here is base 2, and it didn't matter up to this point right here because I had raised it to the 0th power, and so at that point it didn't factor into what I was doing. But now it's important that I should have said that at the start. So I'm picking B equals 2 as my base number. You can pick any base that you want when you're using an exponential function and so clever choice of the base might actually make fitting from point to point be a little bit easier, but I'm using base 2. So I have, when x is 5, I want y to be 2, so 2 is equal to a times 2 to the 5 minus 1 minus a. So remember that constant k turned out to be negative a. However, I'd stuck all these things together. 2 to the 4th power, 5 minus 1 is 4, 2 to the 4th power is 16, so 16a minus a is equal to 2, or a turns out to be equal to 2/15. So 16a minus a is 15a, divide both sides by 15, and it turns out that a is equal to 2/15, which means from the start that k, that constant, when I solve for it right here, k is equal to negative 2/15. And altogether, I apologize for the stumbles as I've gone along here, but you have to think and talk at the same time. So my function that I'm going to put onto my paper is 2/15 of 2 to the x minus 1 minus 2/15. All right, and if you wanted to check values, maybe you can see this is my 4th part of my letter B, that if you substitute in the number 1, this part is equal to 1, so 2/15 minus 2/15 is 0. So that corresponds to the point 1, 0. And when x is equal to 5, 5 minus 1 is 4, 2 to the 4th is 16, 16 times 2/15 is 32/15, minus 2/15 is 30/15 is equal to 2. So I've accomplished my goal. My graph goes from the point 1, 0 to the point 2/15, and that's this function, 2/15 times 2 to the x minus 1. So there's an example of a function we didn't study together in class yet, but it's part of our chapter 7 materials that we'll be studying. My 4th part of my function is 2/15 of 2 to the x minus 1 minus 2/15. And for x's from 1 to 5 and y's from 0 to 2, that exponential function is the function that fits through those 2 points. So the growth rate is 2/15. The x-intercept, or the values had to be adjusted. You saw that was a little trickier than the one where I just had to adjust the growth rate. So here I had to adjust the values of the constant k and the constant h. All right, so let me get back on the stick here. I have one last part of the letter B, and that's to fit the top part of this bottom loop. So I need a function. I'm going to make a function that goes from the point 1, 4 to the point 5, 2. And I decided when I was sitting there thinking just a second ago that I would use the part of a rational function, the part of the function 1 over x. So remember our parent function, the function 1 over x, looks like this, right? To make the bottom part of my letter B, I'm going to use this piece of that rational function 1 over x and make it fit in the values that I want to go from the point 1,4 to the 0.52 here at the end. All right, so one of your challenges in the project was to create put a rational function into the graph, and it says in the instructions that you're supposed to show with dashed lines the asymptotes that are guiding your rational function. So the basic unstretched 1 over x function has asymptotes at x equals 0. So the vertical line x equals 0 is not defined, so that number is a vertical asymptote. And y equals 0 is the horizontal asymptote. So the function decreases as x goes to infinity, but never gets to 0. So you're always dividing 1 by some number in the function 1 over x, and so the value approaches 0 as x goes to infinity, but it never gets there. So y equals 0 forms what we call a horizontal asymptote for that function. All right, so I'm envisioning using this piece of the rational function, and I'm going to fit it kind of the same way I did the exponential function a second ago. I'm going to fit it between this point and this point. I'm going to use that little chunk of the rational function. So on my graph here, I'm going to show that I'm going to shift the asymptotes for this part right here. I'm going to shift to horizontal asymptote of y is equal to 5. I'm sorry, my bad. Can't see. I'm way behind the camera here, so things are kind of awkward for me the way that I'm doing this. And x equals 6 as the vertical asymptote. So on my graph, I've kind of messed it up just a little bit here, but I'm going to put a dashed line at x equals 6 and a dashed line at y equals 5 to represent these two asymptotes of the rational function 1 over x shifted right 6 and up 5. Okay, so just like I did a second ago, here's a little bit of that modeling work. Excuse my shifting things around. But my basic function is going to be y equals some number, and maybe I'll worry about that as I go, over x minus 6. That's to shift the vertical asymptote over here to 6. I'm going to make the function fit from 1,4 to 2,5 inside of that little piece right there. But I'm going to show my vertical and my horizontal asymptotes. I showed them in red there just to kind of demonstrate them. All right, so I'm able to adjust the function by multiplying by a constant a, and like the other one before, I can shift the rational function up or down. So the x minus 6, this part of it shifts the function 6 units to the right, makes that vertical asymptote be at x equals 6. And so now I'm going to do the same trick that I did a couple of minutes ago. Remember my points, I want to go from 1,4 to 5,2. So when I put in x equals 1, I want to get out 4, and when I put in 5, I want to get out 2. All right, so here I go. When I put in 1, I want to get out 4. 1 minus 6 plus k. And this is 4 equals a over negative 5 plus k. So here I have a and k in terms of each other. Let me substitute in the other point and look for a solution here in just a second. So I want to put in y equals 2 into the model, and I get a over 5, so x is equal to 5 minus 6 plus k. So here I put in the 2 points. I substituted them into my basic function that I want to try to fit. So when x is equal to 5, y is equal to 2. It looks to me like this one is going to give me a better solution, or a better jumping. I have 2 equations with 2 unknowns that I'm going to try to solve simultaneously. So it looks to me like this one is going to be easier to work with. So it says that 2 is equal to negative a plus k. So in other words, k is equal to a plus 2. to substitute that into this equation. So 4 is equal to minus 1/5 of a, that's this part, plus a plus 2. So k is equal to a plus 2. Alright, and now I have an equation that only has a's in it. I'm thinking as hard as I can. Plus 2. So negative 1/5 a plus 1a equals 4/5 a. Subtract 2 from both sides. And 10/4 equals 5/2. Turns out to be the value of a. So what I did right there is I multiplied both sides times 5 and divided by 4. So, and then reduced. So a is equal to 5/2. So it looks to me like my function that's going to fit from 1,4 to 5,2, that chunk of the rational function, is going to be 5/2 x minus 6 plus, and I didn't solve for k yet here, so k equals a plus 2. Since a is equal to 5/2, then k must be equal to 9/2. Right, so k equals 5/2 plus 4/2 is 9/2. 9/2. And you can bet that I'm going to excuse me, I'm going to test this to see if it works, and if it doesn't, I'll be deleting this video. So when I substitute in x equals 1, I get 5 over negative 5 is negative 1, so I get minus 1/2 plus 9/2 is equal to 4. So when I test x equals 1, I did get y equals 4. And let's hopefully the other one works as well. When I substitute in x equals 5, 5 minus 6 is negative 1. So this becomes negative 5/2. 9/2 minus 5/2 is 4/2 is 2. So it does indeed, when I put in 5, I get out 2. So this function, and right here, is my fourth. There I just did a rational function. That part, I'm doing a couple of the harder kinds of functions to make on your project. I apologize. But there I have created the exponential function and the rational function. Let me make sure I'm looking at that correct. 5 over 2 times x minus 6. I inserted the asymptotes like I was supposed to, and this goes from 1 to 5 as y goes from 2 to 4. So that little excursion into mathematical uncertainty fitted this part of the function. So there I made it pass through those 2 points I wanted by adjusting those constants that allow you to shift the function left or right. So there I've created the letter B by 5 functions. I kind of denoted them some sort of way. If I was doing this for my final version, I might make them in different colors, or I might make my legend a little more clear. This was a rational function. I did a couple of the harder kinds to fit into your function. Straight lines are easy. Quadratics and cubics are relatively easy compared to the exponential and the rational functions, but I've gotten those kind of accomplished on my list of 20 functions that I have to fit in. And now I'm going to fill in the letter O. Most of you don't know this about me, but a lot of people, they say, well, it's easy not to, nobody ever spells your name wrong, Bob, because your name is B-O-B. It's spelled the same forwards and backwards. Well, that's not exactly true. My name is actually capital B, capital O, lowercase b, and so my middle initial, I'm just going to make a circle. So I'm going to remind you how we made a circle of radius 4. I was just looking at a side graph here to see how this is going to fit. I'm going to make my circle be centered at 1, 2, 3, 4. I'm going to center my circle at 11, 0, or at 11, 4. So here I'm thinking in front of you, so I probably should have had maybe this prepared ahead, but you can see I'm just doing this project on an afternoon where I just wanted to chat with you guys, my friends. So I'm going to put the center at 11, 4 and make the radius be 4. So it'll be 1, 2, 3, 4 units in each direction. And you all remember this is one of the easiest jobs in your whole project, is fitting a circle into the graph. So my capital letter O that I just made right there is made by the function x minus 11 plus y minus 4 is equal to, remember over here you put r squared. My radius is 4, so r squared would be 16. So x minus 11 squared plus y minus 4 squared equals 16 is the equation of the circle centered at 11, 4 with a radius of 4. So there's the capital letter O that forms my name. All right, I'm going to now do something a little bit different in order to fill in the lowercase b. I'm going to make a straight line that goes from the point 16, 0 to the point 28. Okay, so I'll jot that down. I'm going to go from 16, 0 to 28. So I'm making the width be 4 like before, but there's no good reason for that. I'm just doing it. You'll see why. I'm making a non-vertical, non-horizontal line, and hopefully you guys have that down to a science. So what I'll do this here, this is for a couple of you in class, so appreciate as I say this. I'm going to do this as fast like Jack Robinson. So the two ingredients that I need are the slope. So the slope of my line is 8 over 4. So I'm going to go up 8 and over 4. So my slope is 2. Good. Okay, and I think I'll use this point to write the equation on my line. Like I said, Jack Robinson could have hardly done this one any faster. The straight line that goes through the point 16, 0 and 20, 28 is the straight line. 2 times x minus 16. So y equals 2x minus 32 is my function. If you substitute in x equals 16, you get 0. If you substitute in x equals 20, you get 8. So you can kind of see that. And so this non-vertical, non-horizontal line that I have to put into my graph, the one part of this lowercase b, the straight line y is equal to 2x minus 32, or f of x, maybe I should have called it that, equals 2x minus 32 for x's in from 16 to 20. I'll go back and fix my circle. I noticed I forgot to fill in my circle things here a second ago. Y goes from 0 to 8. This is a non-horizontal, so this is a vertical, non-horizontal, non-vertical line. Okay, so let me fill in the domain and range for my circle that I filled in a second ago. The domain and range are 7 to 15 and 0 to 8. So I forgot to fill those in as I was going along there. So 7 to 15. And the y's are from 0 to 8. This is my circle. So that circle, to make my O, I just made the straight line 2x minus 32, so there's that straight line. I decided I would try to fit a square root function, so I thought one more function that I could demonstrate for you today. I'm going to make a part of a square root function that's going to go to the halfway point of this line, and maybe let me do that math ahead of time. So I'm going to start at the point 16, 0, and I'm going to close the loop halfway up this line. So remember, the midpoint of my straight line midpoint is 16 plus 20 over 2, comma, 0 plus 8 over 2 is 36 is 18.4. And that was probably pretty evident, maybe without doing that math, but I thought that would remind you of home a little bit. So the point 18 and 2, or 18 and 4, oh, I kind of missed on my straight line, didn't I? Is right here, the halfway point. So the midpoint is 16, or is 18.4. So I better get back on the beam here. The square root function that I'm going to try to fit as function number 8 on my graph, the lower loop of that lowercase b is going to be of the form a times the square root of x minus h plus k. So this is another one of those functions where I don't have to play any fancy tricks here. I can just adjust the left and right to shift the point that was at 0, 0, and then I can adjust the stretching factor. So there's the basic parent model, and I'm going to shift mine over to x equals 16. That's where the 0, 0 point is going to be, and plus 0. So I'm not going to shift it up or down. So my starting point is going to be at the point 16, 0, and I'm just going to make this square root function fit like that on my graph, just because I needed a square root and I wanted to show you guys how to do a square root function. So maybe that wasn't the best choice. I'd probably rethink it on the final version of my project. So when I put in 16, I get 0. That's pretty obvious that works, but I want it to work at the point 24, or 18.4. So I want, when I put in the number 18, I want to get out y equals 4. So 18 and 4 is the point that I want to get out of my graph. You see I made a little bit of an error when I was graphing there. So let me fix that. When I'm going to try to solve for a, when x is 18, I want y to be equal to 4. So a must be equal to, or 4 must be equal to a times the square root of 2. So a is 4 over the square root of 2. Or as you like to do in rational function land, if I multiply by square root of 2 over square root of 2, I get 4 square roots of 2 over 2, which is 2 root 2. So the constant a is 2 times the square root of 2, and my function that fills in this little square root function, so I can fit any kind of function I want, whether or not it makes good sense. The function is, here it is, y is equal to 2 square roots of 2 times the square root of x minus 16, the end. So x is in 16 to 18, and my y's went from 0 to 4, and this was a square root. And I can use functions repeatedly, so I can use a function more than one time, but you do have a list of at least one cubic, at least one, so there you'll read, as you read the project, you'll see those different things that you have to include. I made my name kind of weird, but I did it in order to kind of show you the thought process for creating the list of functions that spells your name. there's probably some other things that I could go on about. Maybe I didn't put a horizontal line. Let me do that real quickly. How about as a last function, since I didn't demonstrate it, let me put a horizontal line from x equals 21 to x equals 26. So I'll say that as the part of the design I was going to make to use up some of my other functions, I had a horizontal line like I just graphed it for you there from 21 to 26. So my last thing is a horizontal line at y equals 4. So there's my y value. The domain is from 21 to 26 because I wanted a horizontal line in my graph. And my y is only the number 4 is my range. And so this is a horizontal line. So I threw that one in just as a, how do you graph in a horizontal line? That's the way that you would do that. I'm sure we could probably think of some other things to do. This video has probably been way long enough, and in thinking through my issues as I go there, I probably didn't do it as good as I could have done in one sitting. I hope you all will forgive me for that. I'm going to end this now and talk to you in some other video later. Bye.